Okay, so recording is started. You can share the screen if you want.
Okay, please sir, wait. Sanjit sir, doing. Where is it? Right, sir?
Not yet.
Okay, sir.
It's appearing. Now it has appeared. Okay.
Sir, I was starting from this. So instead of calling the correct formula for augmented diagonal of the problem, gain of x by x plus y plus x equal to y. Okay, sir. So what sir, I think this is the x square plus y square in the plane that I do. Plus lambda into this is x minus y. Okay, sir.
Yes.
Plus x minus y height. Why is that? How to compute this?
Oh, this one you are asking. Okay.
Yes, sir. Eighth question. What is actually
So where is this from? Which question is this? Is this assignment or some other subject?
no, this is ADM optimized. That paper.
Okay.
Last week I discussed about paper. That paper.
I see.
But
Okay.
it's important regarding ADM. So it's very important. Augmented language design.
Right. So
Necessary.
I see.
Learn it about.
That extra material. Oh, okay.
Yes, we find here. So everything is here.
Okay, so let's see what's the difference between the first and the third option. It's exactly the same, right?
The first and third is not same. So
Oh, I
plus
see.
plus
There's
and
x plus y. Sorry, yeah, missed it. So of course the C is wrong, right? Because you want x minus y equals to 0, right? That's the constraint. Now in the dual, you want to impose the Lagrangian such that if x minus y is not equal to 0 is not satisfied, then the optimization becomes unconstrained, right? So if if x is not equal to y, then if lambda is, let's say, not equal to 0, and you are maximizing over lambda, so therefore this minimization problem will become infinity. So, okay, so how to explain it better? So let's say, so do you have any question about the plus minus lambda x minus y, or am I explaining it?
x minus y sign. X minus y equal to 0. X minus y. But whole square, I think whole square.
Oh, that is from the slides. So do you have the what do you call the
Slide.
week 8 slides of scalable data science?
Yes, sir, I have.
Okay. Yeah, you can, or maybe I can. Okay. Okay, you start.
I saw you.
Okay, so let's go down one slide at a time. Yeah. Okay, next. Next. Please go on. Yeah, so this part, wait. In the method of multipliers,
Yes, sir.
so maybe go up a bit. Go to the previous slide. Yeah, so you see there is ax minus b whole square rho.
Yeah.
This is that term.
That formula.
Yeah.
That formula.
Yes, this augmented Lagrangian is the first two terms plus rho times whatever the constraint is there.
Sir, rho by 2, what is rho by 2?
Oh, that is a constant term that can be adjusted.
That can be there or no?
Yeah. No. Either plus lambda or minus lambda. One of these will be correct. Right. So you can go back to the slides once again. Let's see. So keep going. So method of multipliers is the inspiration for the augmented ADMM. So let's go down to the ADMM slide now. Keep scrolling. Yeah. So here you see that square term coming on. Yeah. So here you see that the constraint is, so this is the general formula, right? So you have the minimization over fx plus gx subject to that constraint. That constraint is x minus y right now, right? X equals to y. Here ax plus bz is c equal to c. There it was x equals to, let's say, y is c, right? So you have that y is the lambda here. Here Lagrangian is written as y. So there Lagrangian is written as lambda. So you have plus lambda x minus y instead of ax plus bz minus c, you have x minus y. Okay. So there is no plus rho times that by 2 is a constant. So don't worry too much about it. Rho times this thing. Now the key thing that might confuse you was that whether it should be plus y or minus y, because two options have plus lambda or minus lambda, right?
Yes.
So it will be plus lambda. That's the A is not equal to B. Now, do you understand why that should be?
Yes, understood. This will be A. A is the answer.
It will be A, but why should it be plus and not minus?
Plus, because this is
Yeah, so there is a reasoning behind this format. So basically, if you remember, we try to maximize over y, right? We minimize over x and z, and we maximize over the dual variable, right?
Okay. Minimize over y and z and maximize over y.
So what happens when y is being multiplied with this term, let's say x minus y or ax plus bz minus c? If it is not equal, if the inequality is not satisfied, then there is a non-zero value in the bracket instead of 0. If x is not equal to y, then x minus y will be some non-zero value, right? And therefore, when we maximize over y, it will approach infinity. It will keep going up because there's a non-zero multiplication. So the only way for it to not achieve infinity is to have strictly adhere to the equality constraint. So
that it comes 0.
Yes. So if you had minus y, then inequality ke case mein it would have become 0. And therefore, equality will not be preserved. So you cannot have minus there. You have to have a plus, so that any mistake leads to an infinity value. So the formula basically is your fx plus gz term plus lambda times whatever equality constraint is there, plus rho or rho by 2, both are fine, times that again the equality constraint. Okay. Okay. Yeah, so there are 3 parts to ADMM, one at a time. X. So one's for the primal, one's for the dual. So X and Z is. Yes. This is, there are 3 lines here because X and Z are separated for this formula. In that case, in the PDF, I don't know what the formula is.
Okay. I'll let you go some points here. These points are because it's a good question.
Okay, so basically here what's happening is that you have these 3 constraints, right? Which are, so fx plus gz is one constraint, and yt this thing, and rho, 3 constraints. Now you have 3 variables, x, z, and y. X and z are initially there in the equation minimization form, so they are called the primal constraints, right?
Okay.
And y is called the dual constraint because this is what you added on your own to get those subject to things involved, subject to something equal to something that you have folded in by using the y. So dual is y and primal are x and z. Now what
primal?
Yeah, primal variables and dual variables. So these should be there earlier in the slide.
Yeah, dual.
Okay.
Yes, sir. Sir, what I have studied this. Okay, sir.
Hmm.
So xk plus 1 equal to argument we discussed.
Hmm.
First update x variable and then constant.
Yes.
I've gone through the lecture also.
So,
Yes, sir.
okay. Sorry, your voice got a bit low. I couldn't hear you. Can you repeat?
Hello, sir. Can you hear me?
Now
Can
much
you hear me
better.
now?
Much better. Yeah.
Okay. Sir, what happens in the three equations, what I have gone through and understood. First, x updates the x, this first equation, updates and then solves that. Because xk plus 1 nikal gaya, ye xk plus 1 value is coming in z.
Yes. No,
and
not
then
in.
z is updated.
Yeah. Yes, exactly. So in the, like you said, in the first line, we have the x, z and y values from before, xk, zk, yk. Now I want to again update x. So x becomes the variable. I take gradient of the entire thing with respect to x. Here z and y are considered as constants equal to zk and yk. Okay, so only x is the variable. So now I take gradient with respect to x and then find the minimum, and then I basically update it with xk plus 1. And now in the second line, I considered xk plus 1 and yk as the constants, and I take gradient with respect to z. So xk and zk are done. And after these two are done, they are put in the formula, and then the y term is updated.
This is gradient descent, I think.
This is gradient descent, exactly. So in the last term, there is no fx gz because we are only interested in y terms.
Yes.
Right?
Yes.
So everything else will be constant and gradient will be 0. So for shorthand, it's not written. It's just the y terms that are written.
Yes.
Hmm.
So can I come to the question now?
Yeah, sure.
Now it's written that the following update equations are wrong for the following problem. Update equation is xt plus 1. This one is the update equation.
Okay. You have to take the gradient and see what's the thing. So you will have x square plus y square plus you will have the lambda x minus y plus rho square or rho square by 2 whatever times x minus y whole square. Right? You will have that equation here.
Okay, I let me write. Oh, that format.
Yes. So x square plus y square will be the first thing.
Plus lambda into x minus y.
Plus lambda times x minus y plus rho square.
X minus,
rho square x minus y whole square. Yeah. So now you consider y and lambda to be constants and just take the gradient with respect to x. Yeah. So if you derive with respect to x, then you should get.
I'm doing it.
Okay.
Plus lambda plus 2 into x minus y. So if I do derivation, it will come 2x plus lambda plus 2 into x minus y.
Okay.
It's coming like this. Because x square is here, x square derivative 2x, y square is 0. But lambda is x minus y. So lambda रहेगा x का derivative 1 होता है, y 0 हो गया. So lambda हो गया x रहेगा. Plus x minus y का whole square. 2 into x minus y और x का derivative कितने होते हैं? 1 होते हैं और y 0 हो गया. So 2x plus lambda plus 2 into x minus y.
2x plus, let me think, 2x plus lambda plus 2 rho x minus 2 rho y, and then you have 2 rho y minus lambda by 2 1 plus rho. So I am getting minus lambda plus 2 rho y by 2 1 plus rho. Are you getting the same thing?
So let's cycle the equation. So plus y square plus lambda is x minus y. Is it clear, sir? Plus rho I have to write rho by 2y. Sir? Rho by 2, right? It's equal to rho by 2.
Okay, so let's go line by line. Your first line is x square plus y square plus lambda x minus y plus rho x minus y whole square. Okay.
Upon 2 whole square is it? Is it okay?
No, just consider it rho for now. Okay. So now you have if you take gradient with respect to x, x square becomes 2x. Okay. plus 0, y square is 0, plus lambda.
Lambda.
So lambda only, x minus y just will become 1, nothing will be there. Plus 2 rho in bracket x minus y, right?
Yeah, this is fine.
Okay, so now you just take 2 rho and lambda to the right hand side. So you get minus lambda plus 2 rho y, right?
Minus lambda plus minus 2 rho y.
No,
X minus y.
plus. So you have 2 rho x minus y, one. So this is 2 rho x minus 2 rho y. And if you take minus 2 rho y to the other side, you get plus 2 rho y.
Sir, what is I got with plus lambda plus 2 rho equals 1. It's fine.
Yes, yes.
Now, when I'm taking a lambda and 2 rho x minus y to that side, this will be minus lambda is minus 2 rho x minus y.
No, only the y you are taking. X, all the x terms are on the left hand side.
Okay. Understood.
So you take x common and then you
Okay.
just bring everything else to the denominator. That's what you have to do.
Okay. But 2 rho y is going to on that thing.
Only 2 rho y will come to the right side. So you get minus lambda plus 2 rho y, right? So basically, and in the denominator, if you take x common, you will get 1 plus rho. 2x bracket mein 1 plus rho. So the 2 1 plus rho you can bring to the lower part.
On that side.
So basically, you see the form sort of resembles this. There is some mismatch with respect to plus minus, right? Yeah, so that's all you have to do. You have to do this for each of the 3 terms. You will take gradient with respect to x, gradient with respect to y, and gradient with respect to lambda. And you will just see whether the plus minus matches, and whichever does not match, then you will have to sort of mark it.
Fine. It's clear.
Okay.
Now 10th question. ADM is a meta-optimized algorithm. It's fine. I know it is meta-optimized. Is it okay, sir?
So it depends on the definition. I'm not sure if this one has been covered in the lecture, but it's a meta optimization because let's see, it uses other optimizers to solve each step. It can be used for distributed optimization. So it can be used for optimizing non-differentiable functions. So B is definitely correct, right? We have been learning ADMM because it's a distributed optimization problem technique. So I don't know what meta means. I don't know what these, I don't know what the definition of meta was for this course, but we know that B is correct because ADMM. So if you go back to the slide, can you go back for one minute? So why is it no. Okay, just keep at that earlier part.
I'm sorry. ADMM is optimized. But reason for error.
Right. Okay, but why is it distributed? Do you understand that?
That's why that I have gone earlier.
Okay.
ADMM is why sir? Please tell one.
So because it can be used for distributed optimization. So go back to the slide once and please scroll up to that formula where we had the row term fx plus gz thing, those 3 equations. Slightly more. Bus. Okay. Here, keep it here. Okay. So here you see when you are computing xk plus 1, it's using yk and zk and x. So basically xk plus 1 can be computed independently in one machine. Zk plus 1 can be computed independently in one machine. And the last one can be computed in another machine. So basically, given the same gradient computation step, these 3 operations can be distributed across different machines. So that's the advantage of ADMM.
Fine.
Okay. This is definitely true. No. So if it had been true even for the question 10, you would have C being correct, right?
Sir, why also
So if it is non-differentiable, then SGD will not work like that. I mean, it does
Content
not have a
extender.
single global minimum. But you shouldn't spend too much time on something which is not directly related to the course. It's good that you are. Very nice.
This I have solved few questions. I recall. With 17 one.
Okay, okay. So this I think you can do now. Yes. So what is the doubt and why are you confused? After our discussion now, this should be easy for you.
I guess.
Yeah, which? C. Yes, you are right. Yes, so it's the same formula, right? You have something equal to 0 in the constraint. You have the initial fx gx plus rho x1 plus x2 whole square. Same thing as before.
Sir, एक और question है.
Mm-hmm.
Sir, ये तो question suppose if you होता है fx plus cx plus lambda, जैसे lambda x1 plus x2 तो है, ठीक है? lambda का value होता क्या? Greater than 0 होता है या less than 0?
Oh, that good question. Yes. So it will be greater than 0, but Q. Why?
Why, sir?
So again, if you think there, so you want, so for example, यहाँ पे you want x1 plus x2 to be always equal to 0, right? So when it is equal to 0, the value of lambda does not matter. When the equality constraint is satisfied, then the value of lambda does not matter. No matter what value it takes, the optimization problem will remain at the same place, right? Because it's multiplied by 0. Now, if the constraint is not satisfied, if the inside the bracket x1 plus x2 is not equal to 0, if that is the case, then what happens? Then you want to penalize the objective for not adhering to the constraint. How do you penalize it? You increase the loss. And since it's a maximization problem here, in order to increase that loss, you will ensure that lambda will be greater than 0 so that it goes to plus infinity.
Understood. So, sir, might be the question also, in the paper also. They might ask this. Yes, sir. That's why I asked you.
Yeah, this is all related to the concept that is there in the slide.
90, which are the following about NCT and ADM what? ADM and NCT are different methods. Different has.
Yes, both are descent. SGD is the stochastic gradient descent. It has the descent in its name only.
Yes, sir. On the name itself.
Yeah. Both are gradient descent. They iteratively update the parameter values to reach the point of the lowest value.
Yes, sir.
Yeah, I don't think so. You need to worry about this.
It's like trigonometry. It feels like
So basically, yeah, in the method of moments, if you, so for the complete explanation, it's best if you go through the second lecture of that week again. But the idea is that, yeah, this one. So the idea is in the method of, in the method of multipliers. Yeah, exactly. So I think you can go up a bit. Let me see if it's there in the slides. The shortcomings of method of multipliers. Go up a bit. So just go slowly so that. Okay, go up a bit maybe. More please. So when, yeah. Yes, so it's written all drawbacks of dual ascent. Okay. No, that's fine. So here they introduce rho, but above that, if you see in the slide, so it has all the drawbacks of dual ascent. So what are the drawbacks? You have to go up and see. It basically refers to the drawbacks of dual ascent. Yeah. So here you see that if Lxyk, so basically here also they are doing something very similar. They are first attacking X, reducing it, then they're fixing X, and then they're attacking Y, right? Something similar to what ADMM does. But here the thing is, if if the first point of attack, Lxy, is not strictly convex. What does strict convexity mean? It means that it has a one global minimum. So there is only one unique xk plus 1 as the solution to that argument thing, right? That is strict convexity. So if you have a one unique solution of the first argument, that means you can substitute it in the second equation and then you can proceed. But if you do not have one unique thing, if you have multiple solutions, if the first step has multiple options, then you don't know which way to proceed. So then you have to resort to guessing. So that's the thing, that if you have to ensure that Lxy, the first optimization step, is strictly convex. And that is what ADMM does by introducing rho. So if you go through the lecture again or go understand the slides, they will say that yes, this problem is being solved by adding that rho term. Okay. Yes, sub-optimizations are basically that part where they're fixing other variables and attacking only one. Yeah. No, why? Wait. Ah, yes, this is, yes, you're right. Okay, yeah.
Suppose E is convex, yes sir. And P of X whole square is also convex.
Yes.
Why so?
So if you can take double derivative and get the minimum, then it's convex. So that's the way to think about it.
One more question. Sir, what is K in center? U center. K in plus.
Okay.
Probability given. Okay.
Mm-hmm.
So how we are computed? Nowhere in the lecture the how is computed.
Oh, is it? I have to see the K-means plus lecture slides to understand what's going on.
At the end, almost at the end. Clustering and all. Sorry, L2 dot or right question. L2 dot or distance path both are same. What is that?
So L2 norm is one type of a distance. So let's say you have a bunch of points on some, let's say, plane. Let's say you have a bunch of points on the 2D plane, right? So now let's say you have 2 points, 0, 0 and 1, 1. Okay. Now there are many ways you can take the distance between 2 points. So one way is to just take 1 minus 0 whole square plus 1 minus 0 whole squared and square root, right? So that is what's called L2 norm. Another way is to just take 1 minus 0 plus 1 minus 0. That is L1 norm. So basically you are, for L2 norm, you are just taking the shortest path, let's say, and for L1 norm, you are traveling 1 unit to the X and 1 unit to the Y. So one right and one up. So there are two notions of distance here that you can easily see. Now, for any distance function, you can have any arbitrary norm. It's in general, it's called LP norm, but usually we are here dealing with L2 norm. So you will see 2 everywhere, X minus Y whole square and all that thing.
L1, yeah, I think L2 norm is better than L1.
It depends on the application. It depends on, it's actually, you can't say either or any one is better. But L2 is something that we learned from very beginning. So we are more used to it. And also L2 norm has an advantage that it is differentiable. Like you can take the advantage of X square, right? Sorry, you can take the gradient of X square. Yeah.
Right, so what I will
Okay, K means plus plus, what's happening? Competitive, so that it's approximation algorithm, line of F for the classical pick. So in classical K means we pick K points at random. Okay. Then what's happening? K means on Gaussians, you have a bunch. So this here you have a bunch of Gaussian distributions which are very far away. So you have points clustered separately. Okay. Then okay, so there are select centers using the furthest point algorithm to approximation to the K-means clustering.
understood. The farthest point also go center limit and make a cluster in that. Like that, I understand.
Yeah, but what is furthest point algorithm?
Farthest point means that we have to compute the distance from each point, I think, or each of the point, this farthest point. And whichever having the maximum distance, that is the farthest point, I think.
Okay, okay.
Correct, sir. Right, is wrong.
Yeah, so it may be there in the slide that you skipped over. Yeah, so what's there in, okay, fine. Yeah, okay. Okay.
Yeah.
So let dx be the, wait, let dx be the distance between x and the nearest cluster center, and sample proportional to dx is dx to the power a and dx. I see. So so Lloyd's has x as 0. So x. So I have to read through this. I'm not yet confident on this. So, but you are saying that they have not given the formula for dx anywhere. Yeah, so somewhere they will. Okay, so let's take up this question towards the end. We'll give it another try. Yeah.
Yeah, that is the this is the multiplier. This is just a mixed automatic from the convex.
Yeah, so this question we have discussed before, right? Just 1 and 2 were exchanged.
Yes, sir.
Strictly convex thing we have discussed, like that shortcoming of the method of multipliers was addressed by Rho. No, it is true, right? We saw that in the slide. It uses the sub-optimization to address that problem where you had multiple solutions, possibility of multiple solutions, and you want it to be strictly convex. So you use the Rho multiplier, that part.
मैं देखूंगा ये वाला क्वेश्चन ये नहीं हो पा रहा तो अजीब है ये अच्छा आंसर जो होता है इन द स्लाइड लेकिन
So if you Acha, so the first part is clear that you have minimization over fx plus gx subject to ax plus bz minus c equal to 0. That's it.
Right.
So you have xk plus 1 being updated and then zk plus 1. So here, okay, so here you see that xk plus 1 is not used for the zk plus 1 thing, right? So that's why you can combine the first two things. Because if you have xk, zk and yk, then you can get xk plus 1 and zk plus 1 separately or together. You can do both. Right? Because zk plus 1 argmin is not using xk plus 1.
Yes.
So it is possible to combine x and z updates together. So C is wrong.
Not possible to combine.
So yeah, so we can not combine them when zk plus 1 depends on xk plus 1. Right? But since here it does not, since it only depends on xk, then the first and the second things can be combined.
Okay.
So,
First and second, na?
so which now amongst A and B, which one uses row? Do you remember from the slides? Method of multipliers or dual decomposition?
No method of multiplier.
Exactly. So you have got it. So the key thing is to notice that xk plus 1 is not being used. Otherwise, it would not be possible to combine the two updates.
Sir, and sir, dual decomposition बताएंगे sir?
Hmm?
Dual decomposition.
What do you want to know about that?
एक dual decomposition थोड़ा बताएंगे what is happening here?
That's there in the slides, no? We can go through that quickly.
Okay. I'm going over there.
Okay. So dual decomposition is the first thing, right? So how many slides are before that? Just show me once. Nothing else before that. Okay. Yeah, okay. So dual ascent, what's happening? So let's start from dual ascent because it is very similar to that. Right. So dual ascent you have just this thing, you have minimizing x over ax equal to b constraint, and you have no row term here as of yet. So you just have those two things, the fx and the y, Lagrangian times the equality constraint, right? So this part you understand. First we take the minimum over the x part, and then we take the maximization over the Lagrangian. So it's a min-max thing, right? So if you go below, so this is dual ascent because there are two things happening. There's one minimization, there's one maximization. We minimize over the initial, what are called the primal variables, the x, and we are maximizing over y or lambda, whatever are the Lagrangian or the dual variables. So let's go below. Yeah. So what does gradient descent for this do? So basically, again, like before, you are fixing y and you are attacking x, right? So x with xk and yk, let's say you are fixing y to yk, and then you are attacking x, and then you find xk plus 1 by taking argument, right? And then you are fixing xk plus 1 and then attacking y, and you find yk plus 1, right?
Okay, fine.
So this is dual ascent. So you are doing two-pronged ascent, which is for x and y. Okay. So now you have this strict convexity problem, which again we have discussed before. So then if you go down, so what is dual decomposition? It's the same thing as before. The new just idea is that your fx, let's say it is decomposable, right? What do you mean by decomposable? Let's say it's the addition of f1. So you see in the notes, you have seen some objectives looking like fx plus gy, right? Or something like that. So instead of that, let's say fx can be written as f1 x1 plus f2 x2. That's it. So it is decomposable into two parts, or here in general, if it is decomposable into n parts, then basically that loss on the n parts are also decomposable. So if you have a plus b, then loss a plus loss b becomes the thing, right? So basically that's the idea. So for minimization of x, you can split it into those n parts. So this is where so from dual ascent, you are coming to dual decomposition. Here is where the decomposition happening, right? So that is dual decomposition. You just have a decomposable fx and you do the same thing as you did before. So if you go down, I think it's written out.
Dual decomposition, what I understand, it can be two in parts, can be decomposed. Okay?
Right.
Again, the loss can be also decomposed the same way.
This you have got loss part. Okay.
Then it's separate in it. Okay. It will go over there. Now, what is happening to us? into the one.
So n is what? N is the number of functions into which it has been decomposed, right? So over each of those individual functions, you have a separate loss because the loss has also been decomposed. So over those n loss things, you compute the xk plus 1 separately. So the idea is that these things can be done in parallel, separately, distributed way, right? If the function consists of n decomposable parts, then the loss consists of n decomposable parts, and therefore the gradient computation, the argmin, can be done separately in n different parts, right? And then after using all of these n things, in the xk plus 1, you have n values for I is equal to 1 to n. You can combine all of them and get the summation over ai xi, which is required for y. So at the end, you combine them. So here is the, in the distributed solution, it's summarized. You scatter the yk to the individual nodes. What is yk? Yk is basically the decomposed component of. So basically this yk term is required for all xi, right? In the first line, if you see, the yk is there for all the i's. So if you have n different machines, you send them each xi. So you decompose the function and you send each of the n parts to n different machines, right? And then you send a copy of yk to all of those machines because yk is required everywhere. So that's what it's written. Scatter yk to the nodes. Nodes means machines here. Okay. So now in each node, in the ith node, you compute the respective xi. So every machine has a copy of yk and it has that fraction of xi. It has the decomposed small portion of the fx, right? So using that, it can individually compute xk plus 1 and then you gather them. So basically you send back to the source so master machine, whatever, you gather all the AIXI from each of the machines and then you compute yk plus 1. So you got the idea. So dual ascent is simple. I think that's the basic gradient descent, and this is just distributed.
The method of augmentation has two convergence but cannot be parallel. ये मैंने इंटरनेट भी देखा तो ये ट्रू शो कर रहे हैं. It is false. I think.
So, okay, so let's read the sentence again. The method of augmented Lagrangian. What is the method of augmented Lagrangian?
That equation form. That equation form.
So dual ascent, right? Yeah. So in dual ascent, you are augmenting with the Lagrangian. Or is it the row term? Which one do you think?
The Lagrangian is the
row term. Okay, good. So the method of the augmented Lagrangian has good convergence properties, but cannot be parallelized.
It can be parallelized.
Yep. Yes. Sorry, what's your question?
Sir, yeah, that cannot be parallelized. It's a false. It's a statement is false.
So where did you see it cannot be parallelized? Let me just. Let me look at the slide once. One sec. I don't want to. Yeah, just taking 1 minute. Yeah, no, I am opening the slide on my end. Just give me 1 minute. So, okay, 1 sec. So we have method of multipliers, primal feasibility, dual feasibility. 1 second. We are going through the update rules. Convergence stopping criteria. ADMM is a meta optimization algorithm. Yes, it can be.
Can be, sir.
Hmm.
Can be how, sir?
That's what I'm looking, how it is. So the one where we discussed that the X can be computed separately from the Z, and then they can all be brought together to compute the Y. So if you have n decomposable parts, all of them can be computed in separate machines.
Parallel होगी सर.
Mm-hmm.
Sir, parallel होगी ना अलग-अलग में.
Yes.
That statement is wrong.
What is the second part of the statement? Dual decomposition method does not have good convergence properties, but can be parallelized. The dual decomposition does not have good convergence properties because we saw that the unique minimum thing is not there. Strict convexity is not maintained necessarily.
That's true. But can parallelize.
Yeah.
But the upper one is false, I think, sir.
No, it can be parallelized. Yeah.
But the upper part is saying but cannot be parallelized.
Okay, so false then.
I think, sir.
Hmm?
That is false. Sir. Why they are saying it's statement true, it's statement false? I think second is true.
Yeah, where are they saying it's true?
Right, second one is true.
Yes.
And first part is false.
Yes.
It's okay, it's true.
मतलब? Why? This is a question. Why would not they give? Yes, of course. Yes, we have less time, so let's solve that. So can you open that slide or should I? Do you have that slide? Bloom filter wala equation? Yes. We'll solve it now. So week 2, I think. Week 2. Yeah, lecture materials. So go to that part where the Bloom filter equations were. Yeah, almost there. Go down more. Yeah, okay, here. Now go down a bit more. Sorry. Next slide. And then next slide. So here, wait. So here one equation is that if you know m and n, then you can get k, right? Here, this equation you understand, right? ln2, this is a natural logarithm. So ln2 m ln2 by n is k. Okay, this will keep in mind. And now go below. Yeah, here, wait, here. Here you have m if you know n, right? So let's compute that equation. Let's first use, so if you know delta in the right hand side, you can compute m. Yes, yes. So first you use this equation. So first we will use m equals to the ceiling of log of 1 by delta n by log square 2, right?
And upon log of square 2.
Right. Now, what is the value of delta given in the question? Okay. So what is the delta? 10%, right? Okay. So put the value of 10% there. What do you get? The right hand side.
I think it.
Can you show the equation in the screen while you are doing it? Yeah.
Okay, sir, I'm sharing this screen. One second, sharing.
No, it's fine. You can also do it on your own. Just to, it's for me to. Okay, sure.
Let me use my other device.
I cannot see anything yet, but.
Okay, let me cancel from here, then I'll do it.
Okay.
I have multiple devices here.
Appearing?
Okay.
Yes, now visible. Huh. The screen is visible if you are writing. Okay, now it's fine. Okay, good.
Now 1 upon.
Perfect.
10% 0.1.
Yeah.
10 upon log square.
Yeah. So you have to refer to a calculator. What is?
So that also I have available.
Okay.
Online check again. Log of 0.1. Log 1 minus log 10 calculate like this.
You just take log of 0.1 online, you will get it.
Log of 0.1. I directly.
No, wait 1 second. Why is it 0.1? By the way, it is 1 by delta, right? So 1 by 0.1, no? Delta is what? 10% is 0.1. So what is 1 by delta?
It will be 10.
Yeah.
It will be 10, sir.
Yes.
So log of 10.
So what is log of 10? You can.
Log of 10. Log of 10. Log of 10 is 1.
Base E.
Base E. Log of 10. Base E.
2.3. Okay, so let's write 2.3 over instead of that.
2.3 n upon log square 2.
Yeah. Base will always be E, that we have discussed before. Here.
Log 2 ka whole square. Log 2 ka whole square. Log 2 ka value becomes whole square.
Yes.
Log 2.
0.690
whole square.
Yeah. 69 whole square, yes.
69 whole square.
Yeah.
Equal to 2.3 and upon 0.69 whole square.
Don't forget the bracket, the ceiling symbol. That is important.
That I have.
Okay.
0.69.
So what will you get in the denominator? It will be something less than 0.49.
multiply कर लेते हैं 9 9 या 81 1 8 54 I 62 69 is 207 you can say 207 is 221 right 207 to the 414 1 6 7 4 are कितने हैं 0.47 sir
0.47. Okay. So now you have to use the calculator to do 2.3 by 0.47. What do you get?
2.3 divided 0.47. Okay, sir. एक और डिवाइस है.
I can do it for you.
Please, sir, please help me, sir.
Okay.
बहुत हो
You
गया.
can just type it in Google, by the way.
Okay. 2.3.
2.3 by 0.47, right? So it's 4.89.
4.89.
89. Yep.
4.89 N. Is it this?
Yeah. And the ceiling.
And the ceiling. This is important.
So what is the final answer? 5N.
Yes, sir.
5N, right? So let's
5N.
Yeah. So if you agree until this point?
This point I'm agreeing.
Fine. So if you look at the options that you had shown in that
5N is there.
5N is
5N is
there in only one option. Okay. So actually, if let's say multiple options at 5N, then you would have to also compute K, right? So M you have got now. M equals to 5N, right?
Okay.
Now, if you can you easily go back to the slide?
Okay, I'm going, sir. Now, sir, I'm on different machine. How will I show you?
Okay, so
up बोलिए, sir.
let me share my screen then. You stop sharing.
Okay.
Okay, I am sharing, and now let me go back to the slide. Let's see. So it will just take 1 more minute. Right. So now, so you have currently used this formula to get 5M, right?
That I got.
Now, so what you did, you used the value of delta to get the value of M. Now here, you can use the value of M to get the value of K.
M to get a, sir, share the screen.
Huh?
Please share the screen, sir.
I am sharing, right? Can you not see?
No. There is no screen, sir.
1 sec, sorry. I had to give additional permission. So here, so what I was saying is this, now you can see the screen, right?
It's fine.
Okay. So you had used the value of delta in this formula to get the value of M, right? Just now you got 5M. Now what you need to do is you use this value of M to get the value of K. So can you quickly put 5N here and see what you get?
5N over.
Because you got M equals to 5N, right?
5N.
Now N and N get cancelled. So you have 5ln2.
Log 2 base, na?
Log base is ln. So 5ln2, right? So what is 5ln2? Quickly compute.
5ln1.
What?
0.69.
No, ln2 is 0.69. You had told earlier because you took square of that. Yeah. So it will be 9 5 40, 3.45 or something like that, right? 0.69 into 5 is 3.45, right?
Yes, sir.
So what is the ceiling of that? 4.
Right, 3.45, sir.
Yeah. So the ceiling of that is 4. So basically here you have that 5n, 4.
Okay.
So that's how basic. So basically 2 equations you have to use, delta or the false positive red to get the value of m and then m to get the value of k.
Okay, okay. Understood.
Okay. Yeah.
Sir, what's the question, sir? What's the question? No, next time, sir, एक class और
Week 1.
week 1. Basically, what's the question, sir?
So should I go to week 1 assignment 1?
Please, sir.
Okay.
Week 1. I have a question for you.
Which question?
What's the one that the what? Sir, one thing. First question is, आप चलते हो ASPS people. Probability of A, probability B. What is the probability A complexity? Formula you know the okay, sir. How do they get the formula? The formula when it comes to degree.
Okay, so here.
So please, sir, please go to the solution. If the solution is then we can do it. What solution is that? Solve here. That's solve here.
So you are asking this question, right?
So you can clear it at that moment.
Sorry, I didn't understand you. Your voice is
sir, आप week हर week की solution है. Please go to that.
Oh, I see.
Solution is
I see accepted answers. Where is the solution?
Solution. Yeah,
I see. Got it.
देखिए उसको week 1 में देखिए.
Okay, thanks. Okay, got it. Perfect. So you are asking how this formula came? Is it? Hello. So यहाँ पे my suggestion is it's always easy to draw a Venn diagram. Do you know Venn diagrams?
I know that very well.
Okay, so forget the formula. I always draw a Venn diagram and I shade the portions and I try to get it from there. So the circle of A would be 0.25, the circle of B would be 0.45, and the intersection shaded area is 0.1, right? So A complement intersection B is what? A complement is anything outside the A circle. And it intersects with B. That means the part of B that is not there in the A intersection B, right? That moon-like, crescent moon-like part of B. Right. So that, yeah. So it's easy to draw those circles and get the answer. Second is okay. So when can we say that X and Y are independent? So what is when are X and Y? When this X and Y independent means that this condition should hold, right? Intersection should be equal to product, right? So you just have to find the intersection because product, you know, it is 0.12.
Okay.
Right? So what is the intersection? What is the X intersection Y formula?
That one is 0.5.
Yes. So no, 0.58 is X union Y, not intersection, right? So X union complement is 0.42. Therefore, 1 minus X union is 0.42. Therefore, X union is 1 minus 0.42 is equal to 0.58. Right? This you are convinced. Now, X union Y, there is that well-known formula is X plus Y minus X intersection Y. So X plus Y minus X union Y will give you the intersection. So 0.4 plus 0.3 is 0.7. 0.7 minus 0.58 will be 0.12. Right? Right. So X intersection Y, you know, is 0.12. Now X into Y, you know, is 0.4 into 0.3, which is 0.12.
X intersection is 0.58 minus 0.7 is not 0.1.
Why? 0.7 minus 0.58. That is 0.12, right?
Yes.
Good. Okay, so rest of the questions, if you have from this, then we can take next class. Just list them out. Do you have more doubts from this?
Chapman's doubt has come.
Okay, okay. So then let's do it next class.
Day after tomorrow. Tomorrow I'll study.
Let's do it on Thursday then.
Thursday, fine, but
Thursday, same time as now, 7 to 8. But before that, I would like you to just write out by tomorrow all the questions that you want to ask.
everything will be there over there.
Okay,
It
yeah.
will be there. That's
Please mark all of them and we will prepare accordingly. Okay,
okay.
okay.
Thank you.
Thank you. Thank you. Okay,
Thank
bye.
you. Bye. Take care.
I'm stopping the recording now.
Okay, please.